Hello, my name is Ariel Procaccia. I am delighted and honored to give one of two Social Choice and Welfare Prize talks this year. The topic of the talk is democracy and the pursuit of randomness. Let me give a shout out to my collaborators, Kherdus Benadeh from Boston University, Bailey Flanagan, Paul Gueltz, and Anupam Gupta from Carnegie Mellon University, and Brett Hennig from the Sortition Foundation. I want to start with a quote from Jean-Jacques Rousseau, who had this to say about early democracy in England in the 18th century. He said that the people of England deceive themselves when they fancy they are free. They are so, in fact, during the election of members of parliament, for as soon as a new one is elected, they are again in chains and are nothing. So this is, of course, a very dramatic quote, but I think it still captures the sentiment that some of us still have, around engagement and participation in democracy today. But of course, the question is there a different way of doing democracy? Is there an alternative? One intriguing answer to this question is the idea of sortition, which is the idea of democracy built on lotteries instead of elections. Or in other words, the idea of choosing representatives at random instead of through an election. Now, this may sound crazy, but it actually has a lot of historical precedent. The idea dates back to ancient Athens, where some of the most prominent bodies of government, including the all-important Council of 500, were chosen through sortition at random. In the Renaissance, in Florence and Venice and the Kingdom of Aragon, sortition was very prevalent, and again, some of the most important bodies of government were chosen through sortition. But sortition all but disappeared during the American and French revolutions that built these new democracies around the idea of elections and essentially made democracy synonymous with elections. However, in the last couple of decades, sortition has really seen a resurgence in the form of citizens' assemblies, which are randomly selected assemblies consisting of everyday citizens. They're often commissioned by local or national governments, and the goal is for these people to deliberate and reach decisions on important questions and inform policymakers with their ideas. Now, this has been happening on a wide scale in recent years. Let me just give you one example, or four examples out of hundreds. So one kind of very visible example is a constitutional assembly that took place in Ireland in 2016 with 99 participants. The assembly was followed by a national referendum that itself led to changes in the constitution. So this was seen as a very big success story for sortition and citizens' assemblies. In France last year, the president sponsored a very visible climate assembly to discuss climate change with 150 participants. In Mongolia in 2017, they had an assembly consisting of 669 participants to talk about the constitution. And in South Australia, they had a 50-person assembly to talk about nuclear waste in 2016. But again, these are just four examples out of hundreds. I'll give you later two more examples of assemblies where our methods played a role in selecting the participants. So how is sortition done? Ideally, the pipeline for sortition would be choosing the panel directly from the population at random, either uniformly at random or, even better, using stratified sampling, which means partitioning the population into groups and choosing a fixed number of people from each group in order to get a panel that is guaranteed to be representative of the population. However, this is not how things typically work in practice. In practice, you have the population, of course, but to reach out, sortition organizations usually send out letters at random, inviting people to serve on the panel. We've been in touch in the last couple of days with an organization that is reaching out to people by phone and doing random digit dialing, but typically it's done with letters by mail. Now, some of the people who receive a letter opt in and agree to potentially serve on a panel, and they then join the pool of volunteers. And then the final step is that we want to randomly select a panel from the pool of volunteers. Now, the challenge is that the group of letter recipients is representative of the population, and we want the panel to be representative of the population, but the pool of volunteers is highly unrepresentative of the population. Let me illustrate this with an example that will also show you what I mean by representation here. So this is based on data from Climate Assembly UK, a national UK climate assembly that was organized a couple of months ago. It was sponsored by the UK House of Commons, so it was a government-sponsored assembly, and it was run by the Sortition Foundation. The participant selection part was done by the Sortition Foundation using the methods that we'll talk about later. Now here, 60,000 letters were sent. The size of the pool, the number of volunteers, was 1,727. We'll denote that by N and note how small this is compared to 60,000. This is typical. And then the panel size that we denote by K is 110. Now, there are 7 features that the organizers cared about in terms of getting a representative pool. So these are gender, age, geography, education, ethnicity, area, which is urban versus rural, and position on climate change. And what I'm showing you here in these pie charts is the distribution of the feature in the population compared to the pool. So if you look at area, for example, urban versus rural, you can see that the pool is actually quite representative of the population. The proportions are roughly the same. But look at education. The most highly educated people in green are much more common in the pool than in the population. And correspondingly, the people with the lowest level of education in blue are much more common in the population than in the pool. Similarly, if you look at position in climate change, the options here are very concerned about climate change, fairly concerned, not very concerned, or not at all concerned. And you can see that the people who are not very concerned or not at all concerned in green and red have good representation in the population, but are almost not represented at all in the pool, which is not surprising. If you're not concerned about climate change, it's highly unlikely you would volunteer to serve on the climate change panel. So, with this in mind, the problem is the following. We want to select a panel that is representative of the population at random from a pool of volunteers that is highly unrepresentative of the population. How do we do this? So this is something that sortition organizations and practitioners have struggled with, and essentially all of them have invariably come up with some kind of greedy algorithm. Greedy algorithm is computer science terminology for an algorithm that is myopic in the sense that it does at every stage the best thing right now without looking into the future. So I want to show you a particular greedy algorithm that was the one previously used by the Sortition Foundation, but this one is pretty representative. The input to the algorithm on the left is the set of volunteers that in the STO example are identified by 2 features: shape, star or heart, and color, blue or green. So we have 20 volunteers. We have a panel size of 10, K equals 10. And finally, we have quotas, which are meant to ensure that the panel is representative of the population. So in this example, the quotas are, we want at least 4 stars, 4 hearts, 4 blue people, and 4 green people. Now, the way the algorithm works is at every stage, it identifies the feature value with the highest need, where the need is defined by the ratio between the quota that remains to be filled and the number of remaining volunteers in the pool with that feature value. And then once it identified the highest need feature value, the algorithm chooses uniformly at random among the remaining volunteers who satisfy this feature value. So let's see how the algorithm works on an example. Initially, we compute the need for each feature value. So for star, it's 4 over 10 because the quota is 4. We have 10 stars in the pool. Similarly for heart. For blue, it's 4 over 11. And for green, it's 4 over 9. We have a quota of 4 and 9 green people in the pool. So the highest need is for green. So what I'll do is I'll choose uniformly at random among the 9 green people. And I chose this green star that's highlighted in yellow on the right. Now, at this point, what I have to do is recalculate the need for each feature value, in particular, recalculate the need for green and star. So now the need for green will be 3 over 9. We need 3 more. We have 9 stars remaining in our pool. And the need for green is 3 over 8. We have 3 people that we still need to choose that are green, and 8 green people remaining in our pool. But at this point, the highest need is actually for heart with 4 over 10. So I'll go ahead and select a heart uniformly at random from the pool on the right. And right, so I chose the heart. I now need to update the need for each feature value. I get these updated numbers. If you look at them, you see that now the highest need is for green. So I'm again going to choose a green person uniformly at random, update the needs. Now the highest need is again for heart. We choose a heart uniformly at random. And again, highest need is green, and highest need is heart, and then green, and then heart. At this point, we've selected 8 people according to the algorithm. And at this point, we still have 2 seats to fill, but the quotas have been filled. So we have 4 stars, 4 hearts, 4 blue people, 4 green people. We can choose the remaining 2 people on the panel uniformly at random. But the thing to notice is that until this last stage, the blue star, the one blue star we have in our pool of volunteers, had no chance of being selected because the algorithm alternated, remember, between green heart, green heart, green heart, green heart. So evidently, the blue star has a much lower probability of selection than the other volunteers, which seems unfair. Now, you might say, maybe this is something that's inherent to this example because of how the quotas are built. And we'll see in a couple of minutes that this is not the case. Now, you might also wonder, maybe this is just this toy example they have carefully constructed to make the greedy algorithm look bad. Maybe this doesn't happen on real-world examples. But this is, again, not the case. It very much happens. So let's go back to our Climate Assembly UK data. And what I'm showing here is the histogram of selection probabilities for volunteers, for the 1,727 volunteers that you get when you run the algorithm on this dataset. So the thing to notice here is that if you look at the bar at the far left, these are the volunteers with very, very low probability of selection, very close to 0. And you can see that many of the volunteers, around 450, are in that category, are given very low probability of selection by the greedy algorithm. Now, you might again say, maybe this example is such that the quotas forced you to give really low selection probabilities to volunteers. But that's, again, not the case. So here's a different algorithm that I'll refer to for now as a mystery challenger. I'll unmask it in a couple of minutes. When you run this other algorithm on the same dataset, you get the histogram at the bottom, where you can see that everybody is getting a fair chance. Even the minimum probability is kind of bounded away from 0. So everybody has a reasonable probability of being selected. So this tells us that the greedy algorithm is kind of unfair. We're going to revisit this point later. But for now, the question is, how do we get from the histogram at the top to the histogram at the bottom? The key idea is the idea of looking at distributions over panels. So if we go back to our toy example, remember that I promised you that there is a better way of dealing with this example. And the idea is that with probability 1/2, I'm going to choose a panel that consists of the top row of volunteers and the third row of volunteers. And with probability 1/2, I'll choose the second row and the fourth row. Now notice that each of these panels ex post satisfies the quotas. There are at least 4 stars, 4 hearts, 4 blue people, and 4 green people. Moreover, these 2 panels together, their union is the entire set of volunteers. So by randomly selecting between them with probability 1/2 each, I guarantee every volunteer a selection probability of exactly 1/2. I'm able to exactly equalize the probabilities. So this is intuitively the fairest thing you can do and the right thing to do on this example. Now let's spice things up a bit and increase some of the quotas. So we'll raise the quota for star to 6, heart is still 4, blue is going to be 5, and green is going to be 5. The thing to notice about these quotas is that they force me to choose a blue star. Because if I choose 6 stars that are not blue, they're all going to be green, then I need to choose 4 more people for my panel. among the hearts, but that won't allow me to fulfill the quota of 5 blue people. So I have to choose the blue star. But still, under this constraint, I still have a lot of flexibility. So what I propose is that together with the blue star, I'll choose 5 green stars uniformly at random and 4 blue hearts uniformly at random among the 10 blue hearts. So this gives me a distribution over many panels, where each one of them is chosen with probability of 0.00003. However, the selection probability of each volunteer is actually very high. The most unfortunate volunteers are the blue hearts, and even they have 40% probability of being selected, because every time I select 4 blue hearts at random among the 10 blue hearts. So what we saw here is that by eyeballing these simple examples, we can kind of come up with intuitively fair outcomes, intuitively fair distributions over feasible panels. But of course, we want a more general, principled method of doing this. And in order to do that, we're going to draw on a beautiful area that's very close to my heart called fair division. It's a sub-area of mathematics, economics, computer science, political science, and it deals with how to fairly divide stuff according to rigorous notions of fairness. In our case, the thing that we want to divide is selection probability. So what we get is that a distribution over panels of size k divides the overall selection probability of k, for the k seats on our panel, between the pool members. And we kind of think of the utility of each pool member as their selection probability. With this in mind, we can now use some of the tools and ideas developed in fair division in our sortition problem. So this will now allow me to unveil our mystery challenger. It's an algorithm, a mechanism called Lexamen from the fair division literature that's known to have great properties in some applications. In our setting, what Lexamen does is it will choose a distribution over feasible panels that maximizes the minimum probability of any volunteer being selected. Subject to that, there could be multiple distributions achieving this. It maximizes the second lowest probability, then the third lowest, and so on. So in other words, it tries to push the lowest probability of anybody as high as possible. Then, when it got stuck, it pushes the second lowest probability as high as possible, and the third lowest, and so on. When you run this on the Climate Assembly UK data, you get the histogram that we saw before. Now, another option from fair division is called maximum Nash welfare. What it will do in our context is it will maximize the product of selection probabilities of the volunteers. This intuitively, also kind of tries to equalize probabilities, but it shoots for a smoother distribution over probabilities. So if you look at the histogram, you can see that things look a bit smoother than Lexamen. It's also a bit misleading because it may seem that Nash welfare is doing better on the Lexamen objective than Lexamen itself, right? Because the lowest bucket has fewer people, more people are pushed to the right. But this is misleading. In fact, the minimum probability under Nash welfare is lower than Lexamen. They're just in the same bucket. So Nash welfare essentially sacrifices the lowest probability in order to get a smoother distribution over probabilities. So focusing on Lexamen, I want to revisit this idea of being fair in terms of the worst off people, giving everybody a fair chance, and taking an even broader viewpoint. Because so far when we looked at real data, I showed you this one data set, but you might be again suspicious and say, maybe greedy looks bad on this one data set, maybe things are different on other data sets. So again, this is very far from being the case. At this point, we've collected 8 different data sets from citizens' assemblies from 4 different organizations, 5 from the Sortition Foundation, 1 from Off Buy for All, 1 from Healthy Democracy, and 1 from the Center for Climate Assemblies. And what I'm showing here is for each one of these data sets, the purple bar is showing K over N for calibration. So this is the panel size divided by the number of volunteers and gives us the idealized selection probability if we could exactly equalize probabilities, if we could choose uniformly at random. Now, in yellow and green, I'm showing the minimum selection probability of any volunteer under Lexamen and Greedy. And what you can see by looking at Lexamen, the yellow bars, is that Lexamen always gives everybody a fair chance. In many cases, it's even comparable to what you could get if you had no constraints. The Greedy bars in green are essentially invisible. And what this says is that under Greedy, in each one of these data sets, some volunteers have almost no chance of being selected. So this is really a general phenomenon. Now, another thing worth noting is that these algorithms, in particular Lexamen, are very difficult to implement. Computing them is a hard computational problem in a formal sense. And we have quite a bit of theory around an algorithmic framework for computing them, and also some non-trivial engineering tricks to make it happen. But at this point, we've been able to implement these algorithms, and that's led to an open source system called Panelot, which stands for Panel Selection by Lot at random. What it does is it takes as input the pool of volunteers, the quotas, and the size of the panel, and it outputs the Lexamen distribution over feasible panels. Now, this system has been available for roughly half a year now, and it's been used by a bunch of organizations around the world. So in particular, this whole collaboration started from our work with the Sortition Foundation based in the UK. The co-founder and director of the Sortition Foundation, Brett Henning, is a very close collaborator and a co-author on the paper that I'll mention in a few minutes. The Sortition Foundations are the ones that did participant selection for the Climate Assembly UK, and they used Panelot for that purpose. Now, in the last couple of weeks, we've been in touch with an organization in Germany called Nexus that is organizing a visible assembly there, and they have already decided to use Panelot. This will happen in the next couple of weeks. We've also been in close touch with organizations in Poland and Canada, the Center for Climate Assemblies and Mass LBP, mainly at the level of data sharing at this point. And finally, in the US, we've been working with a whole bunch of organizations. One that I want to mention in particular is called Off-By for All. They've used Panelot in order to select participants for an assembly that happened in Michigan in September to talk about COVID-19 policy. And what's been really exceptional about how they used Panelot is they put a lot of thought into how to select a single panel from the distribution given by Panelot in a way that is transparent, in a way that encourages trust in the system. So they came up with some great ideas. In particular, the selection itself, they live streamed it and they recorded it. And what I want to show you is 1 minute from that video in which the presenter explains how they use Panelot in order to very transparently choose a single panel.
So what we set out to do, and what we have done, is sent out invitations to 10,000 randomly selected households across Michigan. Once those of you who were willing and able RSVP'd to us, a volunteer team of computer scientists from Carnegie Mellon University as well as Harvard used an open source algorithm that they developed to generate a list of 1,000 possible panels. Each one of these has a different mix of 30 citizens who again reflect the makeup of Michigan with those proper proportions, women and men, young, old, etc. Now, each of these possible panels is identified now by a unique number, 000 through 999. The three machines that I have here with me, each will select just one digit of that three-digit number. Together, that will give us a three-digit number, and that will be the group of 30 that has been chosen to serve as the panel.
Okay, so let me wrap up with a take-home message, which I think kind of represents this work on sortition, but more broadly represents some of the stuff I've been really excited about in the last couple of years. And it's that computer science and math have a role to play in improving the practice of democracy and potentially in shaping its future. I think this is especially pertinent for the social choice audience for whom this talk is intended. There's so much beautiful theoretical work in social choice. Of course, some of it has been applied, but I think especially now there are so many exciting opportunities to take all of this theory and really put it into practice and influence the trajectory of democracy. This is something I really believe in and something that's really inspired a lot of my own work in recent years. Let me finish with the bibliography. So the work that I talked about is based on a paper with Bailey Flanagan, Paul Gueltz, Anupam Gupta, and Brett Hennig called Fair Selection of Citizens' Assemblies. We're finishing up the write-up of the paper, so it's not available yet. It should be available in the next 2 weeks or so. In the meantime, I want to mention 2 more papers that play a role in the full version of this talk, but I didn't have time to talk about in the 30-minute version. One is a paper called No Stratification Without Representation that thinks about the more idealized sortition pipeline that I talked about initially, where you can choose directly from the population. If you can do that, what's the right way of doing that? The second is a paper called Neutralizing Self-Selection Bias and Sampling for Sortition. This takes a slightly different view of fairness, where instead of being fair to the volunteers, we want to be fair to the population itself. So it's an end-to-end view of what being fair in terms of selection probabilities really means. I'm going to end with that. Thank you so much for your attention.